Okay, so the start of plate tectonics on Earth is similar to the orders of life on Earth in that it's still a debatable subject on when it actually began occurring. Some say that it was between 3.2 to 2.5 billion years ago. Others found that it may be more like a billion years ago. However, researchers in my article, which was called Heading Down Early On, Start of Subduction on Earth, believe that they have found evidence in the Nuvvuagittuq Greenstone Belt that it began more like 4.4 to 3.8 billion years ago. So, just to remind you, we learned in class about greenstone belts, and they are composed of volcanic rocks and sediments that, and they formed during tectonic processes, either during a collision or a subduction event. So now I want to go ahead and give you kind of an overview of what the researchers found, and then go back and fill you in with the methodologies that they used, because I think it'll make a little more sense that way. So what they found was that both the stratigraphy and the trace element composition between the Nuvvuagittuq Greenstone Belt and the Izu-Bonin Mariana Trench are very similar. So at the Izu-Bonin Mariana Trench, I'll call it IBM from now on. That is a convergent plate boundary between the Philippine Ocean Plate and the Pacific Plate. And you will know this because it's where the Mariana Trench is, which is the deepest place on Earth, of course. So it's a subduction zone, right? So if you look at the figure on the left on my poster there, this figure, what it's showing is, on the bottom, it's showing the TI, or the TI to the ZR ratio that they found in the rocks, and then the top one is the THYB to the NBYB ratio. And if you look, the blue dots on there are mid-ocean ridges. The red dots are forearc basalts. And then the green there in the middle is the Archean rocks that we're looking at here. So if you can see just on the chart there that while it's not really representing either the blue or the red, it's kind of there in between, and they are falling within the same sort of ratios as both of those. And actually, that was actually that was done in previous research and not by the researchers in my article. So more importantly here, what they did was, and the article actually didn't really go too great of description of what they actually did, but I read in a different article what they did was they did several dives at the IBM and took records of stratigraphy and then samples and compared to the Nuvvuagittuq Greenstone Belt, which obviously they have easier access to. So if you look there at the figure on the right on the poster, this is showing the stratigraphy. So if you see there the different colors there, they represent the different layers, and on the left is the Nuvvuagittuq and on the right is the IBM forearc, and you can see that the layers match up because they're the same colors, right? So okay, so if you look at it, actually, the there at the bottom, you see that the well, actually, this is something that I learned while doing this, is that the when subduction first begins occurring, it actually starts out more like a well, mid-ocean ridge, in that there's an opening and then decompression magmas. Um, and there at the bottom, that's when we see, at the IBM, we see the forearc basalts, which is similar to the tholeolites that we see at the Nuvvuagittuq belt. And there in the middle, that's showing the uh, trace element patterns that you would see in both of the rocks. And you can see that they kind of, well, they, for the most part, they match up, except for a little discrepancies here and there. And then as you move up and as subduction begins occurring, well, the next layer is when subduction really starts beginning. And well, just to go back, the high field strength elements are common in that bottom layer of the magma, and so in the next layer, much of the HFSEs are being used up. So there isn't as much of those elements left over as we get to the next level and subduction begins occurring. So you can see on the next layer, we start to see a bonanite layer, which is, as the bottom one is high in Ti, this one is low in Ti. And it is depleted in those high field strength elements and rare earth elements. So, as we get into the top layer, that is where they really start seeing the subduction, full subduction occurring. And we see in the IBM that those are the arc andesites, which are low titanium and enriched calc alkaline rocks, which is exactly what we see at the Nuvvuagittuq belt there. And again, if you look at all of the elemental patterns, we can see that they line up fairly closely together. So as for the results, obviously the conclusion that they came to with all this information was that subduction was occurring, but they couldn't really say for sure how fully developed that it was. And the skeptics who look at this data are unconvinced because of the age of those Nuvvuagittuq rocks. And if you look again there at the figure on the right, you can see that they're even questioning on the bottom there that the discrepancies could be because of alteration, because of how old they are. They've gone through metamorphic events. And so this is, if they are in fact right on what they found, this is very significant because this could be where, as we know, this could be an area where life could have began to thrive on Earth, because of, at subduction zones, we see important molecules that could be used as an energy source for early life. And if this is correct, then life on Earth could have existed 4.4 to 3.8 billion years ago. So that is all I have. Thank you.